background. Ai, ai. Ah, ja, mas contar que tá gaysinho pra você. Bem, tudo bem. Tá bem. Você quer colocar três hidrômeros? Tá bom. Não. Colocar um hidrômero para cada parte, né? Ah, eu acho. Não. Ora, senhora. this data. Uh,
Good morning, Professor and class.
Morning. More students coming in. Let's see if I have a simulation here. Okay, so electric motor. Oh, that's the one here. Motor simulation. Okay, that's the one. Okay. Okay, so let's start here. And I'm going to start sharing my screen with you. So last time we were talking about torque in a magnetic torque in a current loop. Okay, I was going to change that. I was going to show you that at the time, but we didn't have any time to do that. This is a simulation, sort of a real life simulation of what happens whenever you have a torque, whenever you have a loop subjected to a magnetic field. Okay, let's see if I can. I like this website. Current. Yeah, I can't. I cannot do what I want to do here. But that's what I was doing before, okay? This is a nice drawing because it has like a 3D model of the loop. So let me slow it down So you can see, yeah, here you go. Okay, so what we have the magnet right here, north polarity, south polarity. This field is a uniform magnetic field. And before we go further, I want to write down here and documenting the okay, simulation of a current loop inside a uniform magnetic field. Okay, so that's the one, and that's what we were doing before, right? We were doing this derivation. So what's happening here? Okay, the blue arrows are the magnetic field. See, blue arrows, the magnetic field. The red arrows is the current direction. Okay, and the black arrows, those two that you see here, are the force, the magnetic force. Magnetic force is also known as the Lorentz force. Lorentz force. So I want you to take a careful look how we determine, right? I'm going to stop the rotation. How we determine the magnetic force from the direction of the current. This current is going in this direction. You have to cross the current with the magnetic field, right-hand rule, right? Palm in the direction of the current, rotates towards the magnetic field direction, and then you get this force, this magnetic force in this direction whenever you are taking the force for this loop along, okay? The magnetic force is gonna be in this direction. And then you repeat that for the other arrow, magnetic current, electric current going to the left, right? You cross that with the magnetic field, and then you get this other force here in this other arm of the loop. Okay, on this arm of the loop, we still have a magnetic force, but it's going to be pulling along the axis of the loop. So there will be no torque whatsoever applied to this loop. Okay, the torque is applied only to those two arms here, those two arms that applies the torque. The net force here is going to be zero, but not the net torque. Here, the net force in this direction is going to be the net force along the axis, right, of rotation of the loop is going to be zero, and the net torque is going to be zero as well. That's what we saw before, right? And notice what's happened. And by the way, this force here depends on the angle that the current loop makes with the magnetic field. Okay, let's move a little bit. Let's see. I'll try to pause it exactly at the moment when the plane of the loop coincides right here. At this very moment in which the plane of the loop coincides with the direction of the magnetic field, what do we have? Do that way. Yeah, the force is supposed this way. Let's see. Yeah, the force, we still have a loop here. We still have a magnetic torque here, a torque given to that. So let's resume. And then whenever it reaches a given angle, notice what happens to the force. Oh, it's right in here. Okay, right in here. So here you go. Here's the battery, right? Here's the battery. Current is flowing. If current is flowing in this direction, right? Current in this direction, you go ahead, do the right-hand rule. You're going to have a magnetic force in this direction and another magnetic force in this direction. But because those two forces are collinear, the net force is going to be 0. But at this very moment, the torque is going to be 0. Okay, because those two forces are collinear. Make sense? Okay, we resume. As the loop passes this position, then the torque, okay, then the torque appears again. The torque comes up again. Okay. The force is always there. It's just that the torque was not there. If I were to revert here, right? Change direction. Okay, change the direction of the battery. Okay. Resume. Okay. So now it's going the other direction. Okay. He took away the arrows, but the force is still there. Okay. He made a mistake of taking away the arrow. The arrow is still there. The force is still there, but the torque isn't. Okay. So I'm sorry. Sorry. The force is not there. Neither the torque. The force here in this direction is not there. And there's a reason for that. That's because this force depends on the angle that the plane of the loop makes with the magnetic field. Okay. And and I'm going to show you a drawing here. That's how it works. Okay. So here you go. The force number 1, right, is the current, the length, the larger length of the loop, the magnetic field, times the sine of this angle here. Okay, when this angle, when the angle between the current and the magnetic field is equal to 0, the force is 0 as well. And then you don't have a torque. You don't have a torque because the force is equal to 0. But as the angle increases, okay, as the angle, and I mean the angle between the normal of the plane, is not, and the magnetic field is not 0, then the torque, then the force increases and the torque increases as well. Okay. My simulation looks just like that. Let's do that. Here you go. Here's the current loop. Okay, I1, I2, I3, I4. Sides A and side B. Oh, I need to start recording, right?
No, you're good.
Am I good? Okay, good. Okay, and okay, so if at this angle here, the top and bottom, right, making an angle. Here's the area vector. Making an angle is the B field. The force is going to be non-zero. Okay. Each of the forces is non-zero, right? But the force here on the arms 2 and 4, the net force is going to be 0. Okay. And again, because those two forces are collinear with each other, there will be no torque whatsoever. It is as though I'm trying to stretch the loop. Okay. The same thing doesn't happen with the currents I1 and I3. Again, we have an area vector right here making an angle with the B field. Okay. Here are the forces in the wire 1 and wire 3. And because those forces are not collinear, they are going to produce a torque on this device. Okay, like that. And you will tend to rotate. Okay. And that force is given by that equation that you saw right here. I, B, B, lowercase b, B for magnetic field, sine of theta. Okay. And when, here you go. We have a torque. Here's my simulation, right? Okay. This force here is going to be 0. I'm even going to, oops, not this one. the force is going to decrease little by little, okay, because of the angle. One more film coming in. Go. Because of the angle between the B field and the vector area. At this point in time, F1 and F3 is going to be 0 because of that angle. Theta, V equal to 0. You know, F1 equal to 0. And the other one equal to 0 as well. And the torque is going to be 0 as well. Consequently, put it here. I made my arrow there, and the torque is going to be 0 as well. Because this force depends on the angle. But, you know, because this this loop has a angular speed, it's going to overshoot this position that's supposed to be the position of equilibrium. Okay, so here you go. You're going to overshoot, but now, you know, the torque is going to revert direction. The torque is going to make my loop rotate in the other direction. Okay, here you go. Component right in here, right? That's going to make the torque in this direction. And it's going to slow down my loop little by little until it comes to omega equal to 0. And then it's going to return, and now it's reverting direction, right? Let's continue with the simulation here. Here you go. Now this guy here changes direction. Format shape. The other one. Let's do this one here. No line. This one here. Yeah, you got this one. I want this one. Yeah, and this one is going to be like that. No, wait a minute. Yeah, that's right. And now the loop is going to revert direction. Okay. It's going to come to this position of maximum speed and torque equal to 0. And let's not forget the omega here is going to be in the other direction. Going to be in the other direction, right? There you go. And now the force is increasing again. I gotta do that. It's increasing again. Unfortunately, that simulation doesn't have it. Doesn't show the force properly. Yeah. This one. I worry about the magnitude of the force later on. Here you go. Yeah. It's rotating and rotating. Okay. Now it's going to start here. Okay, here it starts here. But I need this one as well. is rotating back, and then I must have the last one here. Yeah, I'm having the last one here, which is going to be omega equal to 0. Okay, so that's what happens to my loop, my current loop. If I don't, okay, here you go. You start from rest, start moving because of the torque. I can even put my omega velocity like that. Okay. It passes through this position of equilibrium in which the force is 0, but because of the inertia, the loop is going to overshoot this position of equilibrium, right? Keep on. And now the torque inverted direction as well. Notice that the direction of the torque is contrary to the direction of motion. So the loop is going to decelerate. It's going to reach maximum amplitude at omega equal to 0. And because we still have a torque, but angular velocity equal to 0, the loop is going to bounce back. Okay? Going to bounce back. At this position is going to be, force equal to 0. I'm going to put an arrow very short. And let's not forget, this force is changing according to the angle between the normal and the big field, okay? And we're going to complete a full oscillation, okay? And it's going to keep on oscillating back and forth, just like that. Oscillating back and forth, just like, unless you do something else. Unless you do something else. That's how the story goes, okay? And that's the principle of the electrical motor. That's the principle of the electric motor. Okay? And what is something else that I have to do? Unless you do something else. And that's what the simulation shows here. Okay? And what is this something else? Well, this something else. Let's take a look at the simulation, right? Resume. Here you go. Notice that this loop is not oscillating back and forth just like mine, okay? And there is a reason for that. I'm gonna speed it up. Okay? Okay, see, this loop is not oscillating back and forth. It's going a full rotation, this loop. So there is a little difference between this loop here and the one that I illustrated there. Okay. The difference, I want you to, if you paid attention, right? The difference is in the direction of the current here in this loop. Watch what happens with the direction of the current right in here. At the moment when the torque is equal to 0, what happens to the direction of the current? Okay, what happens to the direction of the current at the moment that the torque is equal to 0? Okay, the current inverts. Do you see that? At this moment, the current is to the right, and now it becomes to the left, right? This current here is right now to the left, but when it reaches torque equal to 0, the current inverts to the right. Okay, so the key here in making this loop go a full circle is this device that you see here. It's called a commutator. This commutator is a device that managed to change the polarities of the loop right here at this input. This polarity doesn't change. The battery remains the same polarity. The trick is right in here in this device that managed to change the current direction in the input at the point of the input of the loop. Okay? So that's the idea of the electric motor. If you don't invert the current, the loop is just gonna keep on oscillating back and forth like my simulation showed. Like my simulation shows here. Okay? So here you go. The situation, we now can tell this story of the electric motor. Remember that's the principle of the where's my notes? Here you go. Physics. Okay. Electric motor. Okay. An electric motor consists of a current loop subjected to a uniform magnetic field. It can also be non-uniform, but it works better with a uniform B field, okay? An electric motor consists of current loop subject to a uniform magnetic field. Okay. In this current loop, okay, two arms of the loop applies a torque to the loop. In this current loop, two arms of the loop. In this device, let's put this like that. In this device, we have four arms, right? All four arms are subjected to a magnetic force. Given by the current value, magnetic field, current value, magnetic field, size of the arm of the loop, and the angle that the area vector of the loop makes with the magnetic field, with the B field, right? So, and I'm gonna electric motor consists of a loop subject to a current loop subject to a magnetic field. Here you go. 1, 2. In this device, we have four arms. All four arms are subjected to a magnetic force, which depends, right? Which depends on the current value, magnetic field, size of the arm of the loop, and the angle that the area vector of the loop makes with the B field. If I'm going to write down those equations, they look just like that, right? Okay. Here you go. Magnetic field is going to be current I L B sine of theta, something like that. Since we have two different arms, right? One loop is going to have a different magnetic force because this L is going to be A, and the other arm is going to be magnetic force is going to be B. Okay, all four arms. Okay, these forces. Note that these forces vary with the angle theta. Okay? When this angle theta is 0, the magnetic force is going to be 0. When the angle theta is 90 degrees, the magnetic force is going to be maximum for both arms. Okay? If we take a pair of these loops, okay, a pair of these arms, okay, opposite to each other, and that's going to be the arm number 2 and 4, right? Four arms number 2 and 4, okay? The torque of this force, the net torque of this force, those are the force values. Okay, I gotta tell you something else before you go there. The net force between all these arms is 0. Net force between arm 1 and 3 is 0. Net force between arm 2 and 4 is 0. Okay, the net force between, let's be specific, right? Between arms 1 and 2 is 0. And between arms, well, not 1 and 2, 1 and 3. And between arms 2 and 4 is also 0. Okay. However, for arms 2 and 4, the net torque is also for arms 2 and 4. The net torque, I'm gonna emphasize here, is also 0. However, for arms 2 and 4 is also 0 because the pair of forces is linear. However, for arms 1 and 3, the pair of forces is not 0, are not collinear all the time. Okay. For this reason, the net torque due to these two arms is different of 0 most of the time. Right? It's different of 0 most of the time. It is this torque that makes the loop rotates with a given angular velocity. However, if you don't do anything, the loop will only oscillate. It is this torque that makes the entire loop rotate, right? Rotate with a given angular velocity that varies with the angle theta. However, if you don't do anything, the loop will only oscillate between a maximum amplitude. Right? Just like you saw here in my simulation. Right, and now go back the other way. Just keep on going that, assuming that there is no losses, no frictional losses, right? This loop is gonna keep on rotating forever, right? Let's see if it is okay, yeah, change direction, reached maximum amplitude, right? Maximum amplitude. For the loop to go a full rotation, okay, you need to invert the direction of the current. You need to invert the direction of the current. At the moment when the torque is changing its direction. Okay. So an electric motor consists of a loop subject to a uniform B field. Let's see if we can improve that. This explanation. You know, this electric motor is full of details. If you're going to analyze it very carefully, with all the details that you need to know to understand fully how it works, you have to go through this process, right? An electric motor consists of a current loop, subject a uniform B field. In this device, we have 4 arms. All 4 arms are subject to a magnetic force. Okay? Then he goes. And then we can go the next step here. This magnetic force, I'm going to put it this way. This magnetic force depends on the following. Here you go. The current value. 2, the magnetic field. The size, the magnetic field, right? The magnetic field, the size of each corresponding arm, of the loop, and the angle that the area vector of the loop makes with the B field. Something like that. 1, 2, 3, 4 parameters. If since I, L, and B are constant, right? Then the force will depend only on the angle theta. Will vary only with the angle theta. Okay. The net force between arms and 3 is 0. And between arms 2 and 4 is also 0, the net force. They have the same magnitude, right? For arms 1 and 3. For arms 1 and 3, you see, this is B, right? Arms 1 and 3 is A. Arms 1 and 3 is A. And just go back to our, here you go. Arms 1 and 3 is A, right? The net force between arms and 1 and 3. Here you go. Is 0. And between arms 2 and 4 is also 0. The net force. Not each separate force, right? If I want to write down the magnetic force for arms 1 and 2, right? And arms 1 and 3, sorry. I have that in arms 2 and 4. Right? One is going to be A and the other is going to be B. Okay, one is going to be A and the other is going to be B. 2 and 4, 1 and 3. 2 and 4 is B, is A. Okay. The net force, the arms number, however, when it comes to the torque, the story is different. When it comes for the torque, the story is different. For arm 2 and 4, the net torque is 0 because the pair of forces is collinear. However, for arms 1 and 3, the pair of forces are not collinear all the time. For this reason, the net torque due to these 2 arms is different of 0. Okay? Let's make sure we go. That's 2. Okay. 2 and 4 right here. Okay. It is this torque that makes the entire loop rotate with a given angular velocity that varies the angle theta. Okay. 8. Throughout this rotation, the torque varies from from 0 from a negative direction through 0 from a negative value, right? From a negative value through 0 until it reaches a maximum positive value. Positive value. Okay. All right, so we're going to do that like that. At time t equal to 0, comma, the torque has its lowest, the torque has its lowest negative value, right? Lowest negative value, and angular velocity equal to 0. So that's what it takes to understand that. We have all those steps that are all encoded there in the equations. A time t equal to 0. Okay, so we're going to do like that. A time t equal to 0, the torque has its lowest value, and an angular velocity and a 0, and a 0 angular velocity. P at the torque, this torque is initial torque accelerates, angularly accelerates the loop, angularly accelerates the loop until it reaches a maximum angular velocity, right? Between A and B, at this point, the torque is 0 and is changing direction. It's in direction in the positive, changes direction and is changing direction and changing its direction. Okay? We can put this way, changing its direction. Although the torque, don't forget, it's net torque. It's not just a time t equal to 0, the net torque, right? Has its lowest negative value, and an angular velocity equal to 0. This initial net torque angularly accelerates the loop until it reaches a maximum angular velocity. At this point, the net torque becomes 0. It goes from a negative value to 0 and from 0 to a positive value, right? And change at this point, the net torque becomes 0 and changes its direction. Although the net torque is 0, the loop do not come to rest because it still has some inertia due to the maximum angular velocity, right? Angular velocity. Due to its maximum angular velocity. As the torque inverts its direction, okay, the loop starts to decelerate. Okay, starts to decelerate. Until it reaches its maximum positive value. It starts to decelerate. It will start to decelerate and decelerate. The torque, the net torque, reaches its maximum positive value. When the angular acceleration, angular velocity becomes 0, right? And the process repeats. And the process repeats back and forth, back and forth. So note that in this case, the loop keeps oscillating back and forth, But that is not how an electrical motor works. An electric motor just keep on rotating in the same direction all the time. Okay? In order to make our loop fully rotated, right? Or make our loop complete a full rotation. We must invert the direction of the current. When the torque becomes 0 and the angular velocity is maximum. So that's the key of the electric motor, which is exactly, and I'm going to show that to you again, right? Can erase that, go right here. Watch this current here direction is pointing to the left, and now it's pointing to the right. Okay, so the torque doesn't invert the direction, and the current must invert in the proper moment. Okay, the current inverts at the moment that the area vector of this loop is either parallel or anti-parallel to the magnetic field. Okay, so that's the whole story about the electric motor. We have that here in the book as well. And by the way, they didn't go through the, yeah, they did some of the details here. Okay. And they have, here you go. Here's my magnetic motor. Do you see that the brush here? That's the commutator device. That's the commutator device that changes the direction of the current that goes through this loop. The shaft, right, which is a rotation axis of rotation. And it is the electric motor that we use in almost every device that we have out there. Whoever invented the electric motor and patented it, must have become a very wealthy man. Nowadays, of course, this electric motor is is in the public domain. Unless someone come up with a non-obvious idea to improve this device, right? Oh, here you go, the battery, right? Current going through the loop, and then we have the torque, all the stuff. Okay, it's 1:38. What I want to do, I want to finish this chapter, and then we have our experiment again, right? Let me make sure we're recording here. Yeah, we're recording. That's good. Magnetic fields produced by currents. And here is the whole idea of the magnetic field. So how a magnetic field is produced, right? the secret behind the production of the existence of magnetic field. What is the secret sauce, right, of the magnetic field, right? What's the secret sauce of the magnetic field? What in reality creates a B field? We do know that there are materials out there that creates that already have an intrinsic magnetic field. Lodestones, the Earth's magnetic field, and the Earth's magnetic field. There are objects out there, right? Objects out there. And the Earth itself, and many of the, not all of them, many of the planets. The sun also, right? The sun and many of the planets. Not all planets have a magnetic field. Mars doesn't have a magnetic field. It's too old of a planet to have a magnetic field. Mercury doesn't have a magnetic field. Let's make sure the sun has a magnetic field. Let's take a look there. Just to magnetic field of the sun, right? Of the sun. Yeah, the sun has a magnetic field. Look here at the magnetic field lines of the sun. Okay. What about magnetic field of Mars? Mars must have a very weak magnetic field. Does not have magnetic field on its own, okay? Outside of relatively small patches of magnetized crust. What about the moon? Magnetic field of the moon. The moon doesn't have all of either. The moon is just like Mars. The moon lacks a magnetic field today. Okay? Jupiter has a magnetic field. By the way, it's said that people say that the magnetic field of the Jupiter is the largest structure in the solar system, even larger than the sun's magnetic field. The stronger the magnetic field, the larger the magnetosphere, some 20,000 times stronger the Earth's magnetic field. So large it begins to avert the solar wind almost 3 million kilometers before it reaches Jupiter. Okay, and what about Mercury? Mercury. Mercury doesn't have, as far as I remember, 1.1% as strong as Earth. Oh, it is as though it has no magnetic field whatsoever. What about Venus? Let's take a look. Venus has no magnetic field today. Okay? So some planets have magnetic fields, other planets don't have magnetic fields. So what's the secret sauce of a B field? Okay? What really creates, what really generates a magnetic field? We do know that there are objects out there that already have an intrinsic magnetic field, like lodestones known by the ancients, the Earth itself, the sun, and many of the planets. So what really, what really creates a magnetic field? It was something that was discovered. Who discovered that? I'm trying to remember. I believe Ørsted discovered back in the 1700s, maybe 1820. He discovered this effect back in 1820. What did he discover at the time? Back in 1820, Ørsted discovered that electric currents produce a magnetic field. So that's the secret way. It took, even though we knew about the existence of magnetic fields since ancient times, since antiquity, it was only 2,000 years later that we discovered we discovered really what produces magnetic field, what are the sources of magnetic field. And the source of magnetic field is an electric current. Okay, so comparison here, right? Comparison. Source of electric field, is an electric charge. Comparison, right? Source of magnetic fields, magnetic charge, which is not magnetic charges, electric current. Sorry, folks, we don't have magnetic charges, right? Second law of electricity and magnetism. Here, okay, electric current. Right? Source of magnetic field, electric current. And that was an electric current, it's just electric charges in motion. 144. That's what you have to know. This is a law of electricity and magnetism. It's a law of electricity and magnetism. A third one. Okay, so let's say even a fourth one, right? So here you go. Coulomb's law. Coulomb's. Let's just slide Gauss's law, right? Which is the electric flux. Electric flux. Okay. Magnetic flux. There is no name for this law. Magnetic flux equal to 0. Magnetic force law, also called Lorentz law. And now we have this other law, right? Magnetic fields are generated by electric current. Also, there's a name for this law, okay? It's encapsulated in Ampere's law. That is encapsulated in Ampere's law. We're going to formulate that. In this part here, we're just going to, in the section, we're just going to study the genetic behavior of the magnetic fields around an electric current, okay? And by the way, there's an important difference between electric field and magnetic field. For an electric field, so that's just one of the differences, right? Another difference between electric and magnetic fields, okay, is that an electric field starts and ends in an electric charge, right? You know, you gotta remember that too. An E field, the charge. Instead, a B field, it doesn't start and end in an electric current. It does not. A B field circulates around an electric current. Can you remember that? Okay. That's part of the law, right? This is part of Coulomb's law. This is part of Ampere's law. See the differences between electric and magnetic field? One needs an electric charge. The others also need an electric charge, but the electric charge needs to be moving. Okay? It's not enough to have an electric charge at rest to generate a magnetic field. That electric charge must be moving. So if you have a moving electric charge, you're going to have a magnetic field and an electric field as well. An electric field that's moving with that charge. On the top of that, you know, an electric field always starts at the positive charge and ends at a negative charge, okay? An electric field, you know, I start at a positive charge and ends in a negative charge, right? negative charge. For now, it's okay to believe that. Later on, you're going to see that's not exactly like that. Okay. But for now, and now that I told you about B field circulate around an electric charge, let's take a look at some types of sometimes of magnetic fields, sometimes of electric current distributions. Okay, so here you go. If you have a current carrying wire, a very long current carrying wire like this one, and by the way, people say that was the experiment that Oersted did. If you place a magnetized needle, a compass around this wire, you're going to see that the magnetized needles, they orient tangent to a circle, to a loop that encloses this current. Okay? That's what Oersted observed. And how do you determine the direction of the magnetic field? Okay? You determine the direction of magnetic field, again, doing the right hand rule. You see how useful the right hand rule is? You point the thumb of your right hand in the direction of the current and rotate the palm of your hand. The direction of the palm of your hand tells you the direction of the magnetic field. Okay? That's how you do it. So here we go. The direction of the magnetic field is determined by the right hand rule. Right hand rule again, but apply it in a different way, right? Rule, apply it in a different way. Okay. So what are the steps? One, orient the thumb of your right hand in the direction of the current. Okay. Let's see. Extend the palm of your right hand and orient the thumb. Your right thumb and orient the right thumb in the direction of the current. The direction you rotate the palm of your right hand is the direction of the field. That's how to find, right? How to find the direction of a B field to a given current. Like that. So, I'm gonna tell you right now, just like the book did, I'm not gonna prove that to you, that there is a relationship for the magnetic field of infinitely long straight wire. Okay? I'm not gonna prove that. Just remember, don't say just remember, just know where to consult the formula, right? But we can derive that mathematically, it's possible, but we're not gonna do that now. Okay, so the B field of the B field of infinitely long straight wire is inversely proportional to the distance from the wire. What you have to know, what you should memorize, okay, is just the proportionality. Okay, that's what the important thing that you have to memorize. The rest is just constants. What else is important for you, to know that the magnetic field is always proportional to the current. Just like the electric field is always proportional, right? To the electric charge. The magnetic field is directly proportional to the electric current. The field of the long straight wire is, and that's what's given here. Mu naught is a constant. I'm not going to write that down. It's the magnetic counterpart of the dielectric constant. We can write that down like that. Mu naught. See? Yeah. Here you go. Mu naught is the magnetic counterpart of the dielectric constant. Okay. It's called, what's the name? Take a look here. Permeability of free space. It's called the permeability of free space. What means free space? The permeability of vacuum. That's what it means. That's one. Okay. And it circulates around the wire. Okay. And then knowing this relationship for the magnetic field, now you can do some simple examples, right? What's the magnetic force that current that the wire exerts on a moving charge, right? If you have this moving charge moving parallel to the wire, what would be the magnetic force, right? Well, if the charge is at rest, the force is zero, right? Magnetic force is zero, but it's moving. And what is moving like tangent, right? To the wire. The wire. At this moment, the charge is moving along this magnetic field line, then it's going to be zero at this very moment. Okay. But in this specific case, that the charge is moving parallel to the current, the charge is going to undertake this helical motion around the wire. What else can you do? Produced by wire, inversely proportional. What else? Let's see. Okay, net force. What about yeah, and then you can use the magnetic force between currents, right? Suppose that you have this wire here, straight wire, and a loop of a current. You can calculate what would be the magnetic force between those two. Okay. What you have to remember is that when the current flows in the same direction, the force is going to be attractive. It's possible to prove that. When the current flows in opposite direction, the force is going to be repulsive. But then he's asking what would be the net force. Okay. What is the answer? A, attracted to the wire. See, this is going to attract this wire, and this is going to repel. But because this one is closer, these two pairs here is closer than this one here, this force here is going to be greater than this force here. Right? Make sense? That's why the answer is A. The magnetic force in this segment is going to be zero. It's going to be zero. And a loop of wire. Here you go. Here's the magnetic field of a loop of wire. That's how it looks like. The magnetic field of a loop of wire is what we call a magnetic dipole, because the field distribution is similar to that of a dipole. Okay. at the center of the loop, it's possible to prove that at the center of the loop, right here, the center of the loop, we're not going to do that. The calculation right now is going to be something like that, where R is this is the radius of the wire. Okay, and how do you get the direction of the magnetic field? Again, you use the right-hand rule, right? You rotate your hand in the direction of the current, and the direction of the thumb tells you the direction of the magnetic field. Okay, so different ways of using the right-hand rule. Different ways of using the right-hand rule to find out the magnetic field. Okay, well, it's already one. Let's see, it's already. Let me adjust my time here. Pacific time. I thought we are gonna be able to finish. It's almost 10 o'clock, right? I thought I was gonna be able to finish, but I didn't. Find the net magnetic field. Yeah, you can find the net magnetic field at the center of this loop. How do you do that? You know, is the superposition of the magnetic field of this wire with the magnetic field of the loop. You know the magnetic field of the loop at the center of the loop. You know the magnetic field of the infinitely long wire. Okay? So the magnetic field due to the wire is going to be upwards, just like it shows here, the right-hand rule. The magnetic field of the loop is going to be downwards, just like it shows right in here. So one is going to subtract the other, okay? And what else we have here? Okay. Oh, the solenoid, that's important. The solenoid is important. The solenoid is the device that produces a uniform magnetic field. Okay, that you have to memorize. The solenoid is one of the most important magnetic devices that we have in there. We use that everywhere. Okay, the solenoid is by the same token, right? By the same token that a parallel plate capacitor produces a uniform field, a solenoid produces a uniform B field. Okay? The symbol, okay, the field of a solenoid is written in there. It's going to be given mu naught I, no matter what device that you have, you're going to have a mu naught there. You're going to have an I in there, and the I is going to be proportional to B. Okay? Mu naught I. Let's see, where is the bell? Mu naught I, and then N. You have this N. And what's this N? N is the number of turns per unit of length. I'm going to write that at N. Oops. N, big N, number of loops divided by L. Okay? Your book, write it down as lowercase n. So if you have to memorize, you should memorize this one here. We have solenoids in our cars. We have solenoids in valves. Have you ever heard of the solenoid valve? Solenoid valve, if you work with agriculture, solenoid valves are nothing but a solenoid that can open and close a passage, okay? For water, a passage for water. For water, for instance. I'm gonna buy one of those solenoids and install here at home. But just to control my solenoid valve, the water that goes there in my water tank upstairs here. I'm gonna do that. So remember that. And there are other applications for solenoid as well, okay? Let's see here. The important that can, the direction of magnetic field, rotate your hand in the palm of your hand in the direction of the current flow. The thumb points in the direction of the magnetic field. That's what this this guy is talking about. Okay, so solenoids are all over the place. You know, magnetic resonance imaging, they have a bunch of solenoids there inside. If you're going to work with MRI in the future, just remember that this device is full of solenoids there inside, and we can extract information from inside of the human body just by using solenoids. Okay, the next thing that we're going to see, oh, you have to do that. Oh, here you go. Current flowing the same direction is attractive. Current flowing opposite directions repel each other, right? Just like I mentioned. And then what we're going to do next is going to be Ampere's law, and we'll finally get over this chapter. Here we need to to work with more care, right? Because it involves equations, and it's not just qualitative knowledge, it's also quantitative knowledge, okay? It's 10:04 right now. I want to take attendance before we go in our break. P07 roster. That's attendance here. Today is #29. Arthur Pacheco, are you there, Arthur? I don't see Arthur Pacheco here. Elika Vafei, are you there?
Here.
Thank you. Next is Brianna Valencia. Oh, Arthur Pacheco is here. Sorry, Arthur. I see you here now. Yeah, I do. Okay. Brianna Valencia. I see Brianna Valencia, but I don't hear from her. I'll put a little star here. Justena Youssef. Ah, Brianna, thank you, Brianna. Justena Youssef. I see Houston is here. Yeah, Houston is here too, but I don't hear from her. I'll put a star. Ashley. Are you there, Ashley? I see Ashley as well. Say hi. Okay, I'm going to put a star here in your name. Ashley. Natalie Espinosa. I don't see Natalie in my list. My roster list. Natalie, nope. Natalie's not here. Next is Jeanette Garcia. I don't see Jeanette here either. Randy Bautista. Thank you, Randy. Noor Hassan.
I'm here.
Thank you, Noor. Kaylee Hernandez. Okay, thank you, Kaylee. Candy Lindsay.
I'm here.
Thank you. Ryan Ong. Are you there, Ryan? Oh, yeah, thank you, Ryan. Donia.
Here.
Thank you. Vanessa Bonilla. Don't forget labs 3 and 4 are due now, right? Blanca Hernandez. Thank you, Blanca. Joshua Jimenez.
I'm here.
Thank you. Alondra. Present. Daisy Mariscal. Daisy, are you there? Okay, thank you. Yesenia. I don't see Yesenia here. Okay, let's put Yesenia here. Labelud. I don't see Labelud either. And we have how many? 14. 2 students didn't answer. 16. Justena, are you there? Ashley, are you there? Okay, so I don't hear from neither one. Let's go for our break. Break from 10:10 to 10:25 a.m. Okay, and just to remind you, lab 3 and 4 are due right now. Let me write down my notes too. Lab reports for labs 3 and 4. Oh gosh, and 4 are due now. Okay. 10:09. What else do we have to do? Today is going to be lab number 5. Okay, 2 resistors. Circuits 2 resistors. No, any questions? There's no questions. Okay, let's go for our break, and I'll see you in 15 minutes. Hello, folks. I'm back here. We're recording now, and I'm gonna share my screen. Good. Okay, so we are here, 29th of March. Oh, next week is gonna be spring break, right? So we're gonna have 1 week of vacation, time off. And by the way, our second exam is the following week, okay? So what have you covered so far? We have covered the 21. Yeah, we still didn't start electromagnetic induction. Okay, so we have, let's put it here, 22. So let's do exam 2. Exam 1, what was the material for exam 1? Exam 1, yeah, we have to resolve that now, right? So you can be prepared for the exam before we start the lab. Let's resolve that now. Okay, so it's gonna be 2 weeks from now, soon after the spring break, right? What I want to do, let's see what let me take a look at the exam, the first exam. Exam 1, first exam. Okay, what did you cover in the first exam? Material for first exam. Okay, 18 and 19 plus lab 1, related notes, 18 and 19. 19. Okay, 18 and 19. Okay, so exam 1 was chapter 18 and 19, right? Plus lab 1 and other stuff. Oh, here you go. It's written here. Oh gosh. Okay, don't need that. Good. Now this one is gonna be 20. Oh, it's not gonna go all the way down to 24, right? It's gonna be to 21. The only thing that's left is Ampere's law. 2021 labs 2. Okay, I'm gonna give you lab 2. I'll give you a break. Okay, I'm not gonna ask for lab 3 and 4. Lab 2 and everything else that we cover, 850. So the only thing that's left here is the material is the last section of 21, which is magnetic fields. Electric circuit should be 2021 here. 2021. Okay. Lab 4 is chapter 20. Magnetic force. That is still 21. Yeah, there's no 22 here. Let's do a list of what's going to show up in the exam. Okay, and just like I did for exam number 1, second exam. See if we have more. No, don't have more. Let goes go down here. Material for the second exam. It's chapter 20, chapter 21, lab 2 related notes. Let's see what are the sections of chapter 20 and 21. This one here. Let's move to the side. Lab 5. We do spring break technically starts Friday. As you see, we can postpone homework after some. Okay. Okay, so let's see. Randy is asking to postpone homework after, Semana Santa, right? Thanksgiving, right? Thanksgiving, spring break here in Brazil is also Semana Santa. Okay, we have been busy with the lab. Instead, we're almost done. We just need a little bit more time. Okay, let's do that now. Spring break technically starts Friday. We have the day off. Go to Shabbos. Yeah, that's right. Let me check. Yeah, let's resolve that lab 5, right? So before we, and I'm gonna change off the date for the homework if you need more time. Lab 5, lab 5. Lab 5. Lab 5 is going to be due. Okay, it's gonna be due on 19th. Lab 5 due. Okay. Lab 6 due. Lab 7 due. And then lab 8 due. Okay. Lab 8 due, and first thing that we have to do here. Let's take a look there at the homework, right? Okay, homework. I put 31st of March. We have 2 more days. So, but that's homework 1 and 2, right? Homework 1 and 2, you're supposed to have finished before the first exam. Everything else is due May 30th. See that? I can give you, let's say, I will give you 1 more week, okay? If it were the homework for chapters 20 and 21, I'll give you more time. But since you will be busy studying for chapters 20 and 21, I'm gonna give you just 1 more week. Okay, March, instead of March 31st, I'll give you the 5th, mid of next spring break. Edit. March 31st. Okay, give you a 7, okay? 7. This assignment, save. Cannot be up. Okay, he doesn't like that for some reason. Gotta go inside, I guess. Edit assignment settings. Yeah, see? That's why. That 7 equals 7. Gone. Okay. So save it. assignment, homework 2. Click here inside. And now we must have assignments. April 7th, April 7th. And the PM. Q. Q. Okay. So April 7th here. And what else we have? We have to take a look here. I want to take another look here for the this one here. Yeah, okay. Wednesday. Good. Okay, so let's write down. Now let's take a look here. Electric circuits. I'm gonna decide. Okay, material second lesson. Chapters 20. Okay, 20.1. 20.2 is a must. Resistance and resistivity. Don't skip temperature dependence. Skip temperature dependence. Okay, electric power. Don't skip electric power. Electric power is important. Okay, alternate current. Yeah, we did cover alternate current. Series wiring. Parallel wiring. 20.8. 20.7. Let's see. Circuit wired parallel. Okay, don't skip this one. 20.8. Okay, we're skipping internal resistance. Okay, so 2010 Kirchhoff's law. You have to know how to use Kirchhoff's law. Kirchhoff's law. Okay, we also covered measurement in that covering the lab, measurement of current and voltage, capacitors and in series and parallel. We covered RC circuit, and that's it. I'm not going to ask for safety and physiological effect of current, but just for safety reasons, okay? Just keep in mind that DC current above 1 amps is, is very dangerous, can kill you. Anything above 1 amp is dangerous. So if you're dealing with regular circuits that you have in your cell phone, that you have, in most small devices, you're never going to exceed 1 amp. It's going to be at most 1/10 of an amp. Okay, the only thing that may hurt in your cell phone is your battery exploding, right? But this, we're not talking if the battery exploded. This is not an effect due to the current. It's an effect due to heat, to explosion, okay? So that's what 220.14 is all about. And I'm gonna put it side by side so you know what I'm talking about, right? Go side by side. Oh, what did I do here? Yep. Okay, this chapter 20 is very extensive. It has lots of material, okay? In a regular course, physics 38, for instance, we usually cover this thing in 3 chapters, not in a single chapter. We usually cover that in 2, 3 chapters. But of course, we cover in a greater depth. Now, what about here? Magnetic force is magnetic field, right? 20.1, 20.2, 20.3, 20.4. Yeah, we did talk about the mass spectrometer. We have the mass spectrometer and we have the velocity selector. Then there are other devices too that this book didn't cover, like the synchrotron. You have the synchrotron, you have the Hall effect. We're not covering that here. 20.5. Looks like everything, right? No, it's not 20. It's 21. Hey, even I'm getting tired here. Here you go. 20.5. 21.5, 21.6, 21.7. Yeah, it's everything. Oh, just 21.9. I don't cover 21.9. Okay, so we stop at 21.8, and I will cover 21.8 next time that we meet. And please, review that on your own as well. Related notes. Let's put here and videos, right? Put this way. Material for the second exam. Skip temperature dependence. Temperature, oh, my goodness. Strange. Did you see that? For somehow my computer started to speak German. That's what it looks like. Yeah, I'm not gonna correct that. Anything else? I guess that's it, right? So, and I have to upload the spreadsheets for lab number 5. Lab number 5, right? We'll go there, PO7. Raw data. Okay, lab number 5 right in here. 10:47. We have 1 hour only. 1 hour and 15 minutes. Go. Okay. One, two, three, 4, 5, 6, 7. Okay. And now we can go to the notes right here. First thing, right? 1. Upload reports for labs 4 and 5. 2. Download spreadsheet for lab. Oh, wait a minute. Labs 3 and 4. 5. Okay, download the spreadsheet for lab 3, 5, lab 5. And I'm going to get another. Let's see. Resistor. Single resistance. Is that the one? No. Must be this one here, 0, 5. Oh. Huh. Okay, so now I want to resistor, must be this one. Yeah, okay, that's the one. Let's see if we have a better one that's better than this one here. Okay. Yeah, okay. Looks like they're almost the same. Yeah, okay. Yeah, they're almost the same. That's okay. So how many students we have so far? 16. So the first thing is 7. Whether you download it. Arthur Pacheco, have you downloaded the spreadsheet? Oops, go ahead. Yes, okay, good. So, Elika, have you downloaded the spreadsheet?
Yes, Professor.
Good, thank you. Brianna, you download the spreadsheet? Yes, good. Justena, are you there, Justena? Have you downloaded the spreadsheet? I don't see Justena here in my list. Huh? Okay, so now, and Ashley Diaz, are you there?
Yes, I'm here.
Okay, did you download their spreadsheet?
Yes, I did.
Okay, yes, 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 yes. Natalie, are you there, Natalie? I don't see Natalie. Next, Jeanette. Are you there, Jeanette? I don't see Jeanette. And Randy. Did you download their spreadsheet, Randy? Yes, thank you. Ah, it's uploading. Okay, I'm gonna put it working. Okay, Noor Hassan, did you upload the spreadsheet? Yep. Okay, thank you. I'm a little bit slow today, just like everybody else, I'm also burned out here. Haven't been sleeping very well. Today I slept well, yesterday I didn't sleep as well. But even though I slept well today, I'm still, a little bit slow here for some reason. It's so bad when you sleep very badly, right? So let's go for Kaylee. Are you there, Kaylee? Okay, good. You just did you download their spreadsheet? I'm asking if you're downloading the new spreadsheet, right? Yeah, here you go. Kennedy, did you download their spreadsheet?
I'm restarting my browser because I'm having trouble even opening the option to download.
Okay, so I'm gonna put a working here. Okay, Ryan, did you download your spreadsheet, right? Is Ryan there? Downloaded, good, thank you. Donia, did you download their spreadsheet?
Yes.
Good, thank you. Vanessa, did you download their spreadsheet? Yeah, good. Blanca? You know what the
Yes.
question, right? Good, thank you, Blanca. Joshua?
Yes.
Good, thank you. Alondra?
Yes, I did.
Okay, good. One more, no, two more. Daisy?
Yes, I did.
Good, thank you. What about Yesenia? Is she here? I don't see Yesenia in my list. And Labelud? Did
Yes,
you,
I download the spreadsheet.
you downloaded?
Yes.
Okay, so I'm gonna put attendance here for you. 16, we have, good. So I'm gonna open one of those spreadsheets and walk you through. Okay, lab 5. You go. Good, so that's the data that we have right here. Well, I'm going to point out what is raw data, what is result. I'm going to start, I'm going to start showing you what's in a different color, right? Blue, I'm going to put the raw data in red. So you identify, here you go. VSUP, the current, V1 and V2. They are all raw data. All of that here, this one here, V total is also raw data. Because we measure V total in the actual, this one is an equation, this one is an equation, so the result. So everything that you see here is raw data. Everything you see here. I'm gonna highlight, it's better to highlight just the measurements, okay? Everything that you see in blue is raw data. This is, this is not raw data. Whatever you put here is not going to be raw data because it's going to be what you get from your experiment, okay? I'm going to walk you through how you perform this experiment. The first thing that you have to do, well, what are you going to do? We're going to choose 2 resistors, and we're going to put those 2 resistors in a circuit. They're going to be connected in series, just like we have been talking about. Now we don't want this one here. We want the other one. This one that we want. Okay, we're going to connect those 2 resistors in series. I'm going to show you how you connect this. That's how it's connected in series. Okay, and then we close the circuit. I'm going to explain to you what this thing is all about. Okay, and then but that's how you connect those 2 resistors in series, right? And that's the diagram schematic. That's the diagram schematic of the 2 resistors in series. And that's how you do in real life. Power supply, battery can be your battery too. Okay. But before you connect those 2 resistors in series, you're going to measure their value. Their value using the multimeter. Right? You're gonna get the digital multimeter, you're going to get adjust the digital multimeter to read the resistance value, and that's what this red key is all about. Remember, it's a multimeter. You have to choose what that device is going to measure, right? You can choose to measure voltage, you can choose to measure resistance, you can choose to measure other things too, current, and so on. Frequency, this one you can measure frequency, DC voltage and AC voltage. Okay. We have the jacks here, black banana termination to black jack, clamp red alligator to one end of the resistor. You gotta connect the resistor in series with this multimeter to measure its resistance to the other end. It's something like that. It looks like something like that. That's the multimeter. A simplified drawing of this multimeter here. Okay. And then you repeat that for resistor number 2. You do that with resistor number 1. Repeat that with resistor number 2. Okay, so let's notes. Okay, lab 5 procedure, and also have lab 5 materials, right? What do we use? Okay, resistor 1, 2 resistors. Let's put it this way: 2 resistors, 1 digital multimeter. Digital multimeter. One digital multimeter. So the first step is measure the resistance of each resistor with the DMM. Lab 5 procedure. And once you measure the resistance of the resistors, you are going to have those 2 values here. Okay? This one is 346 and the other one is 220. Okay, we're going to use that as comparison term, for the sake of comparison. And let me write also the objective of this experiment that I didn't write, right? Objective of lab 5, you know, verify Ohm's law experimentally using a circuit with 2 resistors in series, right? That's the idea. And let's not forget, okay, this is not an actual law. There are lots of things that we call law that are not laws in reality. Okay, there are and remember, there are very few laws in physics. 1 digital multimeter, good. Oh, what else do we need? You know, at least 1 black cable, right? As we go through the procedure, okay, I'm gonna keep on changing. 1 red cable with banana, right? Termination. Here too, 1 red cable with banana termination, 1 black cable with banana termination. Also, what we need, 2 alligators. 2 alligators clip, 2 alligator clips. The alligator clips, what are they used for? The alligator clips are used to grab the end of the resistor. Right in here. Okay, in order to grab the end of the resistor, you use an alligator clip. Those alligator clips are quite common in the labs. Let's take a look here in the alligator clip. Not for the hair. Here you go. Is an alligator clip for. Oh, okay. They look just like that. You know, you can open them. They can secure. That's another way. You know, which is a more expensive alligator clip. You know, it's fancy. I don't like this one. We have only those ones there in the lab. This one is nicer too. It's nicer. See that? It's more sturdy. Here's another alligator clip, different alligator clips, and just to grab the end of the resistor. This end goes to the multimeter, right? Red to red, black with black. Plug in there in the multimeter, and you take the measurement. You know, secure the alligator clip. Secure the resistor with the alligator clip. And here's another version of the alligator clip. That's something that you can take out from the banana from the banana termination. You connect to the banana termination and take it out. I like this one. I like this one because you know, sometimes it's convenient to have this end with the banana clips. Okay, let's see if we have more. That's all you have. But now you have an idea how those alligator clips look like, right? Here you go, more alligator clips here. More alligator clips. Okay. And I didn't illustrate the alligator clip here. What else? Okay, now we are going to let's see. Wait a minute, that's not the right one. Is it? Let me see. Maybe it's this one. Yeah. Okay, maybe it's this one. Use most sensitive scale. Every time that we make a measurement, we use the most sensitive scale, right? And now disconnect everything, disconnect the multimeter from the resistors, and start from scratch. Power supply. Okay, that's another device in our list of materials here. Materials and devices, right? And equipment. Materials and equipment. One power supply. One power supply, and then go here. Okay. Red and black. And this, sometimes they make it yellow, sometimes they make it green. They don't have a standard for that, but there is a standard for that. For the positive, this is the red color, the negative is the black color, right? That is standardized throughout the world. Red cable to red jack of the power supply. Red banana cable to red jack of the power supply. And then you connect. Here at the end, we have the alligator clip. That's what the arrow is all about. Connect the alligator clip to the resistor. And connect the second resistor to the first resistor. And close the circuit. Okay? And close the circuit. When you can either touch one end of the resistor to the other one, or we can use a very convenient device that is sold out there, is mass manufactured. I have many of those. Unfortunately, I don't have any of those here. It's in my other place. Using a proto board. Okay. So we're going to put the proto board in the list of equipment and materials. Proto board. Okay. Proto board to connect the resistors. Okay, so 2 resistors, 2 alligator clips. Measure the resistance of each resistor's DMM, right? Procedure. Start with the power supply. Red banana cable to red plug of the power supply. Okay, of the power supply. Okay. 4. Other end of the banana cable. Let's see what we're going to do here. We're going to get the alligator clip to the other end of the banana cable. Connect, clamp, not connect, clamp, alligator clip to the end of resistor 1. Let's make a distinction, right? Between resistor 1 and 2. 2 resistors. Resistors 1 and 2. Measure the resistance of each resistor. Clamp alligator clip to end of resistor 2. Fix. Plug the other end of resistor 1 to one of the holes of the proto board. Prototype board or proto board. Let's take a look at a proto board, how it looks like. I believe you already saw that before, right? So here, prototype board. Board, it's not prototype board, is just a prototype. Okay, here you go. That's one of them. There are several formats, okay? This one is far more convenient than those ones here. They're still called prototype boards, even though this one is more convenient. You know, it looks just like that. You know, you plug in your resistor in one of those columns. The column that I'm referring is this one here. That's the column I'm referring. This one, those rows here, you leave for something else. Okay? You plug your resistor to one of those rows. And that's what you have here in my drawing. Close this one. Oh, save. Long way. Okay. Going back to the, okay, plug the other end of the resistor onto one of the holes of the prototype board. Plug the second resistor to another hole, to a different hole, right? To a different hole of the proto board. That is in series with the first resistor. Those proto boards are built in such a way that if you want to connect this resistor to this other one in series, you have to connect them in the same row, okay? If you connect this resistor in any of those other holes here, you're not going to make a connection to the other resistor. So basically what we have here, you have a metal plate behind those holes here to make the connection. It is as though if we had a wire connecting this end of the resistor to this other end. Okay? And those proto boards are very convenient. If you have a very convenient to use, and everyone buys something like that. If you're starting working a project that you need to have a circuit, a rough circuit, a prototype circuit, so you use those prototype boards. Okay. These other circuit boards that we saw here, that they also call proto boards, you know, they're not as much convenient because you have to solder them. Okay. You have to apply solder, and it's not just plugging there in the hole. You have this copper here. You have to actually solder it with an iron, a solder iron. Okay, so next, plug the second resistor to a different hole of the proto board that is in the series with the first resistor. 8. You know, connect black cable to the black plug of the power supply. Okay. And connect the other end of the black cable to the free end of resistor 2 using a alligator clip. Okay? Alligator clip. And again, that's what's going to look like when alligator clip is here, alligator clip is here. And that's how the circuit looks like. Once you turn on the power supply, a current is going to start flowing through this circuit. But it's not everything that you need to do the experiment yet. Okay. Here you go. Here's the current flowing. Set the power supply to 10 volts. Set the power supply to 10 volts. Set power supply to 10 volts. And let's take a look at the, let's see, here you go. V supply, 10 volts, right here. We're going to start taking measurements. We're going to start taking the measurements at 10 volts. Okay. The power supply is a device that has a multimeter inside it. So it's going to show here 10 volts in the screen for you. Okay. Now we're going to get the ammeter, the digital multimeter, and set it to read volts. But it's not AC volts, it is DC volts. Every ammeter has those options. Sometimes when you see an instrument like that, you see so many buttons that you get lost, you know? You feel kind of intimidated by the complexity, by the number of buttons in there. Okay, but don't let that scare you. Don't let that scare you. And we are going to make measurements in DC volts. Okay. Measure V total. And how do I measure V total? V total, what do I call V total? V total, I call it the total voltage across those two ends here of the resistor, okay? Don't forget that the voltage is being split by the resistor. Total voltage of 10 volts is going to be split by first resistor, depending on the value of the resistor, is going to be a given voltage, and the second resistor as well. That I'm going to call V1. The voltage across this resistor I call V1. The voltage across this resistor I call V2. But the first thing that we do is to measure the total voltage, just like we see here in my schematic, circuit schematic. Okay, the multimeter is being connected in parallel. Okay, and let's go here. Set power supply to 10 volts. Set DMM to read DC volts. Okay. Connect DMM in parallel with the two resistors. In parallel with the two resistors. And so at this point, we added a black cable. Now we have two black cables to make the measurement, and we added a second red cable, two red cables with banana termination. And these are the measurements. See, that's the V total measurement. Okay, so we set the power supply to 10 volts, and then here you go. I wanna keep track of the measurements that we're making, right? Here you go. Keep track. We set the power supply to 10 volts. The power supply has an internal voltmeter that indicates to you, but we also measured the voltage across the two resistors, which should be very close to the voltage of the power supply. Okay. And again, parallel with the two resistors, read the voltage indication in the DMM. Voltage indication in the DMM, okay? Then what's next? Okay. Then what you're going to do? Now you're going to measure the voltage across this resistor 1, and then the voltage across the resistor 2. Okay. There you go. Use most sensitive scale. We always do that. That's how it looks like. Measuring voltage, always in parallel. Oh yeah, you have to invert the voltage to, you have to invert the cables here. Invert the cables to get a negative measurement of the voltage. Invert cables of the power supply to get. I'm gonna close this one, I don't need that anymore. Invert cables of the power supply to read, to feed, not to read, but to feed a negative voltage to the circuit. So what's that measurement is all about? Well, it's here in my spreadsheet. See, minus 10 volts here, minus 10 volts is here as well. Okay, so I measured the largest one and the lowest one, right? The largest positive voltage, the lowest positive voltage. And your device is going to read the negative voltage. Disconnect everything and start from scratch. You know, measure V1. That's what I tell our students to do. You don't have to disconnect everything. You know, all you have to do is to move the voltmeter there if you're in a hurry. Okay. All you have to do, you know, compare that here. See that? That's what we had initially. So if you're in a hurry to do this experiment, you don't disconnect everything. You just move the probe of the black probe to the middle of the two resistors. Okay. And that's going to be our V1. But if you have time, you want to learn a little bit more, you're going to disconnect everything and connect all over again. That's the type of thing that requires practice to understand what you're doing, right? And the more you practice, the better you become at that. Here you go. Two resistors in series, and then you invert, right? Invert here the cables from the power supply. Okay, so measure V1, the voltage across the second resistor. Okay, invert the polarity, positive value, positive voltage. Invert cable supply, you know, and then before you do that, reinvert the cables after this measurement, after the previous measurement. Measure the voltage across the second circuit, invert the polarity, and take the negative measurement. Like that. What does it look like? No, I'm gonna show you the other one. Here you go. Now what are you doing? We are measuring voltage 1, which is the positive, and voltage 2, which is the negative. In parallel with resistor number 1. Okay. That's where those measurements come from. And next. Now, again, you don't need to disconnect everything, right? All you have to do is to move the connection, the parallel connection that you had with resistor 1 with resistor 2, okay? You go. That's what we had with the measurement for V1, and that's what you're going to have for the measurement with the V2. Okay. Let's see if you have, oh yeah, that's the V total. That's the first one that we measured. That's the second one we measured. That's the third one that we measured. Okay. Invert the cables. Invert the cables after the previous measurement. Measure the voltage across the. You have to put second here. No, it's supposed to be first, not second. Sorry. Now this one is the second. positive voltage, invert the polarity, and take the negative measurement across the second resistor. Okay, and going back here to our drawing, right? That's the measurement that you took now. That's the measurement that you took now. The last measurement is the more difficult one. That's why I leave that for the last. Is to measure the current. That's when people burn the multimeter, burn the fuse of the multimeter. That's when people do that. Because it's so complicated sometimes, okay? And here we go. Now you have to start from scratch. Now you have no choice. You have to start from scratch. Power supply, cable, and get your ammeter in series. Okay. And now there is a specific, a specific plug that measures only current. Okay. See that the ammeter is now in series. Connect to the resistor. I prefer, let's see, so you can. Yeah, I'm going to delete this one so it looks nicer, right? Measuring, I'm going to measure, and always connect in series. Positive, yeah, good. So I don't need that anymore. Delete it. Good. Connect the second resistor and close the circuit. See the difference? Ammeter is in series, voltmeter is in parallel. Okay. Now I'm not gonna write that down all the details, Connect, remove, remove voltmeter from circuit and connect ammeter in series with the circuit. I'm not gonna go into the detail otherwise, right? We 1126. We have the circuit closed. Current is passing through the ammeter, goes through the resistor 1 and resistor 2, and we're gonna make measurements. And that we are doing that with 10 volts, right? We're doing that with 10 volts. When you do that, and then after doing that, measure current, it's gonna be a DC current. Then you invert the polarity again to get the current flowing the other direction. And you're going to see that the current that flows in the other direction has almost the same value than the current that goes in the positive direction. Here you go. Those are the two measurements that you're going to get. One is a positive value, the other is the negative value. That's how we do this expression. And then what you do next? Then you change the voltage supply by your power supply. From 10, you bring down to 8, right? Take the total measurement, V1, V2, the current, to the negative values again. Just repeat what you did, right? Change to 6 volts. Take the total voltage, positive and negative. V1, V1 negative, V1 positive, V1 negative, V2 positive, V2 negative. Current positive, current negative. I forgot to highlight this one. Okay? And so on, until you get to the minimum voltage that you can get, until you complete everything here. Until you complete everything here. Okay. Here is already programmed to do to sum V1 with V2. By the way, when you sum V1 to V2, it should be almost the same as those values here, and almost the same as those values as well. And what do you have to do? There are 3 graphs that you have to do. There you go. Now we finally got to the point where you have to do something, right? Plot, plot V total in the y-axis and current I, right? Current in the x-axis. 3 graphs, V total. And what do I mean by V total? I mean the measurement V total. Equal, not this one, should be this one here. Okay, the measurement V total, this one here, and I. Plot those two. First graph. Then second graph, V1 and I. Third graph, V2 and I. Okay, that's what you have to do. Plot V1 along red would be better along the y-axis. Okay, it's the same current, it's not a different current. And finally, V2. Okay. Okay, now I'm gonna give you the slope of the first graph. Should be close to R1 plus R2. R1 plus R2. The slope of the second graph should be close to R1. Okay. The slope of the third graph should be close to R2. If they are not, that's because you did something wrong or you don't have good data there. 1130. That's what you have to do. Right? Once you plot those graphs, you get to fill up these cells, right? And then don't forget to document the slope here. V total, V1 and V2. What we have, like 100% here. Yeah, 200. So someone is trying to get in Vanessa. Okay, good. Is that clear? 1130. So let's take another break, right? Let's take a 10-minute break. So we have another 20 minutes when we come back. Yes. So break from 11:32 right now to 11:42. And then let's round it up to 45, 11:45. And if you want to stay working that, and then we use the remaining 15 minutes to see if you have any questions, okay? Any questions before you go in the break? Okay, if you don't have any questions, I will see you in what? Yeah, in 13 minutes. Now it's already 12 minutes. I'll see you in 12 minutes. Okay, thank you. And I'll pause here the recording. Back here, so okay. Yeah. So how are you doing there? Let's go quickly through some of you. Make sure that you don't have any problems. The idea here is to plot 3 graphs. Plot 3 graphs, right? Were you able to plot the graphs, Arthur? Arthur Pacheco? Yeah, okay. Did you so plot the graphs, get the trend line? What about your percentage difference? Did you get your percentage difference there? Right here, V total, V1 and V2. I suspect there's a mistake here. Let me check. J4, J5, J4 absolutely. H51, H51. See, H51. Okay, the H51 minus J4, J5. Yes, okay, R1 plus R2. Now, what about downstairs? J4. Well, what percentage are you getting there here? What percentage are you getting here, Arthur? Here in the delta, right? You put this slope here, and then you're supposed to get the. Can you hear me, Arthur? I got 31%. Let me see. 31.10. Sounds a little bit high. 31% for this type of experiment is high. Let's see if I'm getting the same problem. Trend line, display equation chart, 558.4. Let's see. 558.4. I'm getting 1.6%, okay? So, okay, so the equation is correct. I thought the equation was incorrect, but it's not. You are group number 1, right, Pacheco? Let me check if I'm getting the same value there that you're getting. This look on the wrong spot, okay. Okay. So, okay, so that must be the reason, right? Most likely you put the slope right here instead of here, right? So, okay, that's good to know. So I'll get back to you. Let me go through another member to group number 2. I'm going to skip everybody else in group number 1 because we're running out of time, right? Let's see, Natalie, are you there? Oh, Natalie's not here. Okay, so the only one in group number 1 is Ashley. Hi, Ashley.
Hello.
Hi. Okay, so did you plot all the 3 graphs, Ashley?
Yes, I did.
Okay, did you take? Did you also get the percentage difference for all the 3?
I'm inputting them right now. That's
Okay.
the D, right? In that bottom table.
Let's see. One minute. Let's go back to my spreadsheet. Nope, this one. Which one? This one. Here you go. So here you go. So you plot V total and I, right? Got the trend
Yes.
line, and then you input the slope right here for V total. In this one.
Okay.
That's H51. And then you plot V2 and I get the slope, and you write down right in here on G51, right? And so on.
Okay, so for those for V1, the percentage difference I got was 1.0129.
Okay, that's good.
And then for V2, I got 0.4124.
Really good. Okay. And V total?
And I got 1.0649.
Okay, cool. Anything below 5% is good data, okay? If you tell me that, well, like 10%, I would feel for this type of experiment, for this type of electrical experiment, anything below 5% is good data. More than that, I start to suspect that the data is not good, okay? That's the nice thing about those experiments. You get very low percentage differences. Okay, too late. Okay, next here in number 3. Number 3's, let's go for Noor. Noor, did you get your 3 graphs? Ashley just got it. Let's see. Okay, good. How are the percentage differences that you got? Okay, you didn't get so far, right? Okay, so it's still working. So it's still working. Here you go. Next. Let's see, group number 4, right? Donia, did you get your graphs, your 3 graphs?
Yes,
Okay, did you get the percentage differences as well?
I'm still working on it.
Still working, okay. So next one, let's see. Nope, student's not here. So Alondra, did you get your plots, your 3 plots?
Yeah, I did.
Okay, what the percentage difference that you got?
That's what I'm working on right now.
Okay, it looks like I skipped group number 5, right? What about Vanessa Bonilla? Did you get all the 3 plots, Vanessa? Vanessa is not here. Okay, let's see, Vanessa. I'm going to put it all here. And Blanca? Okay, did you plot out the 3 graphs, Blanca?
Yes, sorry. I had to step away, sorry.
Okay. Okay, did you plot the 3 graphs?
Yeah.
Okay, what is the percentage difference you got from those graphs? So maybe the question should be, did you get the percentage difference, right?
Professor, this is Joshua, part of group 5. Yeah, we got the percentage difference.
Okay,
For V1, we got 2.2873.
okay,
For V2, we got 0.0285.
wow.
And then for V total, we got 0.6275.
Okay, good. So you got good data there. And we have 5 more minutes to go. And Lebilud, did you plot all the 3 graphs?
Yes, I was able to plot the trigger. Yes.
Yeah. Okay, and did you get all the percentage differences?
Yeah, I was working on that right now.
Want to work on that? Okay, good. So 4 more minutes to go. So
Professor,
yeah,
could I go over the data for group 3 with you?
yeah. Let's see, Lindsay. Yeah, you plot all the
Yes,
3
sir.
graphs.
Yes. So
Okay.
for 1, the delta is 0.0180.
Okay, 0.02, right? Okay, what about the others?
Okay, V2 is 1.6460.
Okay, and the other?
V total is 1.3282.
Okay, so everything is less than 5%. You're in good shape there.
Okay.
Okay,
right.
that doesn't look like you have anything wrong. And anybody else? 4 more minutes to go.
I actually have a question.
Who is that?
It's Ashley from YouTube.
Okay.
I just wanted to ask you about the R squared really quick. I put the trend line and I displayed the R squared value on all the charts, but they all say 1.
Okay, so you have to fix that, right? There's a way to fix that in Excel. So let's do that together. This one, no, it's not this one. I want this one here. Okay, so here you go. You're going to most likely gonna get a very high R square value, right? And so how do you fix that? Let's plot it together. Here you go. See if I have the same problem. Let's see if I can duplicate the same problem. Yeah, my R square. Okay, I didn't go to 1. Which group are you, Ashley?
Group 2?
Group 2. Okay, so let me get your.
Professor, it's the same thing with our group 1. We're
Yeah.
also getting one. I'm getting 1 on all of them.
Yeah, you have to change the number of decimal places there. It's not difficult to do that. Let me plot all 3 here for group 1. Hopefully I can reproduce the same problem that you are having there, right? Here you go. That's going to be for V1 or either V1 or V2. I am okay. Oh yeah, see, I'm getting R square equal to 1, right? Right? That's because this number is very close to 1, right? How do you fix that? I'm going to walk you through that. We'll have 2 more minutes. Click here the box. You must highlight the box. Right click on the box. And let's see here. And let me try it again. Font, maybe it's here. No, it's not here. Let's see. There's a format trend line. Format trend line label. Okay, you gotta go to format trend line label. Okay, let's do that again. That's the trend line label, right? So when you right click, you go to format trend line label. Okay, once you go to format trend line label, you have to add more decimal places there. Okay, so you're gonna do like number, okay? And now my number that was 1, well, now became 1.00 because I choose 3 decimal places, right? 2 decimal places. I put 3 decimal places, I still see 1, right? So I have to add on the decimal places there until I see a number that's not 1. If I put 6 decimal places, now I finally get R squared that's not 1, right? If I put 5 decimal places, I get this value. I put 6 decimal places, right? I get this value. So here you go, right? So it's a number that's very close to 1. So that's why you are getting that R squared equal to 1. Okay. That goes for everybody else. So if I undo it, yeah.
Professor?
Yeah,
And so that number is what we would input into the R square,
that's right.
correct? Even
Uh-huh.
if it's a longer decimal place, right? Okay.
Yeah.
And then for the confidence level,
Uh-huh.
I had a little bit of trouble with the last lab figuring out the confidence level because it was the same situation.
Uh-huh.
And so because it was so high, would 1 minus 10 to the negative 7 be the max and the minimum?
10 to, okay, so let's get the confidence level here, right? We're gonna do an example
Right.
here.
And I didn't get to check for this data, but I was specifically referencing lab 3. I apologize, lab 4 data.
Okay, here you go. Now, here you go. Now, here you go. We have, let's see, you have 6 data points, right? Let's say you have 6 data points. And then you get a number that's more than that, right? Maybe
Right.
that's what you're referring to, right?
Yes, sir.
Okay, what does it mean? It means that our R square is anywhere between this value here and the maximum value of R square, which is not on my table. The maximum value of R square is 1, okay?
Okay.
Okay, so your value is somewhere between this here and, to the right of this table. So your value is lying some here.
Okay.
Then you go upwards, that will be the lower bound of my CL, right?
Okay, so then we would just put in 1 for the maximum?
Yeah, that's right. That's all you
Okay.
can do, right? There's nothing else you can do, right? Because you don't have them, right?
Okay. Would that be points off for the last lab? I wasn't aware of that. Or would I be able to change that?
Yeah, go ahead and
Or-
change. But do it.
That's okay.
Do it
Okay.
right away. Yeah, do it right away.
Okay, I'll do that right now. Thank you so much.
Anybody else? 1202, right? And okay, we can stop here, and I'll see you again in 1 week and a half after the spring break. Thank you.